Hello and welcome to section 2.4 on continuity. Everything in this video will build upon the intuition for limits that we developed in section 2.2. A common misunderstanding of limits occurs with many calculus students. When they learn about limits, they wrongly believe that the actual value f of a influences the existence or value of the limit of f as x approaches a. It is natural to expect the limit and the actual value to coincide. Take, for example, motion. If you were to look up and notice a large object directly above you that appears to be falling directly towards you, you would move quickly away from your present location. You would naturally expect the object to follow the path it's been on while you've been observing it. We expect continuity. That is, we expect the limit of the object, the motion just before your current observation, to equal the actual value. The dictionary describes continuity as uninterrupted flow, and that is what the mathematical definition guarantees. A function f is continuous at x equals a if the limit as x approaches a equals the actual value f of a. That is, we have an uninterrupted flow from the location of the point at x equals a to the one implied by the trend of the previous points. The limit equals the actual value. An intermediate step towards continuity is one-sided continuity. If the actual value equals the left-hand limit, the function is continuous from the left-hand side. If the actual value equals the right-hand limit, then the function is continuous from the right. In this graph, the function is continuous from the right at x equals a, but it is not continuous at x equals b. The function is continuous from the left at x equals b, but is not continuous at x equals a. Like with limits, the two-sided concept is supported by the one-sided. The function is continuous at x equals a if and only if it is continuous from the left and the right. We say that a function is continuous on an interval if it is continuous for every point in that interval. Visually, a function is continuous on an interval from a to b if the curve is unbroken. That is, if an ant is to crawl along the function, dragging a pen behind itself, it would trace out the graph of the entire function on the interval. For example, take the graph y equals 1 over x. The function is continuous on the interval of infinity to 0 and continuous on the open interval 0 to infinity. In other words, y equals 1 over x is continuous on any interval that does not contain 0. If a function is not continuous at a point, it is called discontinuous. What does it take to be a discontinuity? Well, let's start with what it takes to be continuous. From our definition, to be continuous, the limit and actual value must exist and must be equal. With this in mind, we describe the general types of discontinuities that stem from breaking either 1, 2, or 3. In both graphs, there is a removable discontinuity at x equals a. A removable discontinuity is the case where the limit exists but is unequal to the actual value. This leads to two graphs, one in which the actual value exists but is not equal to the limit, and another where the actual value does not exist. We use the term removable because we can make it continuous by redefining the value of f at x equals a to equal the limit. The next graph shows a jump discontinuity at x equals a. A jump discontinuity is the case where the one-sided limits both exist, but the two-sided limit fails to exist. Notice that the ants can only meet at x equals a if they jump to another level. Our last graph shows an infinite discontinuity. An infinite discontinuity is the case where at least one of the one-sided limits is infinite. The type of discontinuity is not defined by the actual value. It is defined solely by the limit. You've seen the basics. Now work towards mastery through practice and study.